Welcome to another deep dive. Today, we're diving into the world of AI.
Oh, fun.
Yeah, exploring this really cool paper about a new approach to GANs. That's Generative Adversarial Networks.
Right.
If you've spent any time on the internet lately, you've probably seen some of the amazing images they can create.
Oh, yeah. Absolutely.
Like photorealistic pictures of people or objects that never actually existed.
It's true. GANs have really become popular for their ability to generate such realistic data.
Right. But they also have a bit of a reputation for being difficult to train.
Yeah.
And they often rely on kind of hacky solutions. This paper we're looking at today is trying to change that with a simpler, more elegant approach called R3GAN.
And that's what's so intriguing about this paper.
Yeah.
They're proposing a move away from these complex, often ad hoc methods that have been the norm in GAN research.
Okay, so before we get too deep, let's make sure everyone's on the same page. Okay.
We've got articles and research notes you shared with us about R3GAN, and we're here to kind of help break down the key takeaways.
Sounds good.
So to kick things off, can you give us a quick rundown of the basic problem this paper is trying to solve?
Well, one of the biggest challenges with GANs is something called mode collapse.
Mode collapse.
Imagine you're training a GAN to generate images of different types of flowers.
Okay.
But instead of capturing the full diversity of flower species, it gets stuck producing only roses.
Only roses.
Yeah, no matter what you do, you just keep getting more roses.
Interesting.
That's mode collapse.
Okay.
The GAN fails to capture the full distribution of the data it's supposed to learn from.
So basically it's like the GAN has a creative block.
Yeah.
And it can only come up with one idea.
Pretty much.
And this mode collapse thing, I'm guessing it's a major roadblock.
Absolutely.
In GAN research. It's a major hurdle that researchers have been grappling with for years. A lot of the existing solutions involve adding complex tricks to the training process, but those often lack a solid theoretical foundation.
So what is it about this new paper that's different? How are they tackling this mode collapse issue?
That's where their new loss function comes in.
Okay.
They call it regularized relativistic pairing GAN.
Regularized relativistic pairing GAN.
Or RPGN plus R1 plus R2.
RPGN plus R1 plus R2. Got it.
It sounds complicated.
Yeah, a little bit.
But the key takeaway is that this loss function is designed to explicitly encourage the GAN to generate a wider variety of outputs.
I see. So instead of just telling the GAN, make something that looks real, this new loss function is saying, make something that looks real and different from what you've already made.
Precisely. And what's really exciting is that they've actually proven mathematically that this loss function leads to better convergence during training.
Okay, wait, hold on. Break that down for me.
Sure.
Why is that mathematical proof thing so important?
Well, in the past, researchers often had to rely on trial and error to find the right set of tricks to make GANs work. It was very much a see what sticks approach.
Right.
But with this new loss function, they have a theoretical guarantee that it will help the GAN learn more effectively and avoid getting stuck in those mode collapse ruts.
So it's like they've created a more reliable engine for the GAN.
The great analogy.
One that's less likely to stall out.
And they demonstrate this quite convincingly in the paper.
Okay.
They tested their loss function on a particularly challenging data set called stacked MNIST.
Stacked MNIST.
It's basically a data set of handwritten digits arranged to have 1,000 distinct clusters or modes.
1,000.
Which makes it very susceptible to mode collapse.
Wow.
Many traditional GANs struggle to generate all 1,000 modes.
But not this one, right?
Well,
what were the results with this new approach?
As you might expect.
Yeah.
RPGN plus R1 plus R2 achieved full mode coverage.
Full mode coverage.
Meaning it was able to generate images representing all 1,000 modes of the stacked MNIST data set.
That's impressive.
This is a significant achievement because it shows that their loss function is capable of overcoming the limitations of traditional approaches and pushing the boundaries of what GANs can achieve.
So they've got this new loss function that's mathematically sound, helps prevent mode collapse. What else is going on in this paper?
Well, they didn't stop there. They realized that this new loss function was so well behaved that it allowed them to simplify and modernize the entire GAN architecture.
Okay, so walk me through that. How did they actually change the architecture?
So they started with a popular GAN architecture called Style Jan 2.
Style Jan.
And systematically stripped it down.
Okay.
Removing all the unnecessary components.
Interesting.
That had been added over the years as workarounds for issues like mode collapse.
It's like they decluttered the entire system.
Exactly.
Got rid of all the unnecessary baggage.
And once they had this stripped down version, they incorporated modern architectural ideas from convolutional neural networks, or CNNs, things like ResNet architecture, grouped convolutions, and inverted bottlenecks.
Wait a minute.
Yeah.
ResNet architecture, grouped convolutions, inverted bottlenecks.
Right.
These sound like pretty technical concepts.
They are.
Can you give us a quick explanation of what these things are?
So ResNet architecture is a way of designing neural networks that makes it easier to train very deep networks. It helps to prevent a problem called vanishing gradients.
Vanishing gradients.
Which can make it difficult for the network to learn effectively.
Got it.
Grouped convolutions, on the other hand, are a way of making the network more efficient by reducing the number of computations needed.
Computations,
And inverted bottlenecks are a design pattern that allows the network to learn more complex features with fewer parameters.
Okay, so they're basically taking these proven techniques from the world of CNNs and applying them to GANs.
Exactly.
And the result of all this is?
They created a new simplified GAN architecture that they call R3GAN.
R3GAN.
And despite its simplicity,
it
achieves state-of-the-art results.
Really?
On a variety of image generation tasks.
That's amazing.
Yeah.
So even though they've simplified the architecture, they're actually getting better results.
Yes. And not only that, they're also achieving these results without relying on some of the questionable techniques that other methods use to artificially inflate their performance on metrics like FID score.
Yes, the FID score. Yeah. I'm sure some of our listeners might be wondering what that is.
Good question.
Can you give us a quick rundown?
So FID score, or Frisch on Inception, is essentially a measure of how similar the images generated by a GAN are to real images from a given data set.
Got it.
A lower FID score means the generated images are more realistic and closer to the real ones.
Got it. So the fact that R3GAN is achieving these impressive FID scores without any of those questionable techniques means that its performance is genuinely better. Yeah. It's not just a trick with the metrics.
It's a testament to the soundness of their approach.
I'm starting to see why people are so excited about this paper. It's like they found a way to make GANs more powerful and more reliable. At the same time.
And that's why this work is so significant.
Yeah.
It has the potential to change the way we think about and develop GANs in the future.
So they tested R3GAN on a bunch of different data sets, right?
They did.
What were some of the highlights of those results?
Well, on FFHQ, which is a data set of high-quality human faces, R3GAN actually outperforms Style Jan 2.
Really?
Which is impressive, considering Style Jan 2 was already considered a top performer.
So they're beating the previous best with the simpler architecture?
Pretty much.
That's quite a statement.
It is.
What about other data sets?
They also tested R3GAN on CIFAR-10.
CIFAR-10.
Which is a data set of small images of objects, like airplanes, cars, and dogs. And again, they achieved state-of-the-art FID scores, even with a relatively small model size.
So not only is it more effective, but it's also more efficient.
It seems so. And they even got promising results.
Oh, wow.
On ImageNet.
ImageNet.
Which is a massive data set of over 1 million images.
Right.
R3GAN surpassed some larger diffusion models in FID scores while needing significantly fewer function evaluations.
Okay, so we've talked a lot about the technical details of R3GN. We have the loss function, the architecture, the impressive results.
Right.
But before we move on,
sure,
I want to make sure we connect all of this back to our listener.
Good idea.
What's the significance of all of this for someone who might not be a deep learning expert?
That's a great question.
Yeah.
I think one of the key takeaways here is that this research shows that we don't always need to make things more complex to make them better. Sometimes simplification and a strong theoretical foundation can lead to even more impressive results.
That's a powerful message.
It is.
And it goes beyond just AI or computer science.
I think so.
It's relevant to so many fields.
Absolutely.
All right, so we've covered a lot of ground in this first part of our deep dive into R3GN.
Right.
We've talked about the problem of mode collapse, the new loss function that helps address this issue, and the simplified and modernized architecture of R3GN. Wow. But there's still so much more to explore
for sure
in the next part of our deep dive.
Okay.
We'll delve deeper into the implications of this research and discuss the potential impact R3GN could have on the future of AI.
Sounds good. It's funny. For so long, researchers have been piling on complexity in GANs, thinking that was the only way to get better results.
Right.
This paper really challenges that assumption.
It's almost like they're saying, hey, let's step back and rethink the fundamentals.
Exactly.
And that's so refreshing to see. Yeah.
In a field that can sometimes feel obsessed with the latest and greatest, most complex algorithms.
This focus on simplicity and theoretical grounding could really open up new avenues for research. Instead of getting bogged down in tweaking hyperparameters and trying to stabilize these complex architectures, researchers can focus on exploring new ideas, new applications for GANs.
Speaking of new applications, this paper focused on image generation.
It did.
But it makes me wonder, where else could this approach be applied?
That's a great question.
Could we see similar advancements in, say, music generation or text generation?
I think that's a very real possibility.
Yeah.
The principles they've outlined here, simplifying the architecture, focusing on a well-designed loss function.
Right.
These ideas could be transferred to other domains.
Where GANs are being used.
Imagine being able to generate entire musical scores that are both original and stylistically consistent.
Yeah.
Or crafting realistic dialogue for virtual characters in video games.
That would be amazing.
Possibilities are pretty exciting.
And it's not just about creative applications either.
Oh, okay.
GANs are also being used in fields like drug discovery.
Wow.
And material science. Imagine being able to design new molecules with specific properties or generate new materials with unique characteristics.
Interesting.
A more stable and reliable GAN could accelerate progress in those areas as well.
This paper almost feels like a call to action for researchers to explore these new frontiers, to take these principles of simplicity and theoretical grounding and apply them to a whole range of problems.
I think that's a great way to put it. It's like they've laid the groundwork for a new era of GAN research.
Now, it's important to acknowledge that the paper does mention some limitations of R3GN.
Sure.
For instance, while it excels at generating images from scratch, it's not yet equipped for tasks like image editing or generating images with specific controllable features.
That's true.
Right.
However, those limitations don't diminish the significance of this work.
Okay.
Think of it like this.
All right.
They've created a really solid foundation.
Right.
And now it's up to the research community to build upon it.
Right. That they've provided the blueprint.
Exactly.
And now others can come in and add the bells and whistles, the specialized tools for specific tasks.
Exactly. And that's the beauty of research.
Yeah.
It's a collaborative effort.
Right.
With each new discovery.
Yeah.
Building upon the work that came before it.
So, taking a step back from the technical details, what do you think the lasting impact of this paper will be on the field of AI?
I believe this paper has the potential to shift the paradigm in GAN research.
Interesting.
It could steer the field away from this pursuit of ever-increasing complexity and toward a more principled, theoretically grounded approach.
That's a really compelling thought. It's like they're saying, let's not just throw more compute at the problem.
Right.
Let's actually understand how these models work.
Exactly.
And design them in a way that's both effective and elegant.
Precisely. And that shift in thinking could have a ripple effect throughout the field, leading to more robust, reliable, and ultimately more useful AI systems.
So we've talked about the potential benefits of R3GAN.
We have.
Both in terms of its technical advancements and its broader impact on the field of AI.
Yeah.
But I think it's also important to consider the potential downsides, the potential risks that come with any powerful new technology. What are your thoughts on that?
That's an important point.
Yeah.
While this paper doesn't delve too deeply into the ethical considerations, it's crucial to acknowledge that any technology capable of generating such realistic data can be misused.
Imagine the potential for creating deepfakes
that
are even more convincing and harder to detect.
Absolutely.
This could have serious implications for everything from online misinformation to political manipulation.
Absolutely.
And it's not just about deepfakes. There are concerns about bias being embedded in these models, potentially leading to the generation of images or other data that perpetuate harmful stereotypes.
I agree.
It's a reminder that as we develop these increasingly powerful AI systems, we need to be thoughtful about the potential consequences.
Absolutely.
And work to mitigate the risks.
I agree.
We need to build safeguards into these systems, develop mechanisms for detecting and combating misuse, and engage in open and honest discussions about the ethical implications of this technology.
I completely agree.
It's a responsibility that falls on all of us, researchers, developers, policymakers, and society as a whole. We need to ensure that these powerful tools are used for good and not for harm.
Absolutely.
All right. I think that's a really important point to end this part of our deep dive on.
It is.
As we move forward with developing and deploying AI systems. We can't just focus on the technical advancements. We also need to be mindful of the potential social and ethical implications.
Absolutely. Progress without responsibility is ultimately unsustainable.
We've covered a lot of ground today.
Oh, yeah.
From the technical details of R3GAN to its potential impact on various fields, and finally to the crucial ethical considerations that we need to keep in mind.
For sure.
We're almost at the end of our deep dive.
Okay.
But before we wrap things up, I want to touch on one more interesting aspect of this paper. One thing that really struck me about this paper was how they emphasized the importance of theoretical grounding. It wasn't just about building a GAN that worked. It was about understanding why it worked.
Yes, that focus on theoretical understanding is what sets this work apart. For a long time, GAN research has been very empirical. Researchers would try different things, see what worked, and then try to explain it after the fact.
Interesting.
This paper flips that script.
It's like they're saying, let's start with a solid theoretical foundation.
Exactly.
And then build our models on top of that.
I agree.
Which makes a lot of sense.
It does.
If you understand the underlying principles, you're more likely to build something that's both effective and robust.
It reminds me of the difference between just knowing how to bake a cake and actually understanding the chemistry behind it. If you understand the chemistry, you can not only follow a recipe, but also adapt it. Create new recipes and even troubleshoot problems if something goes wrong.
That's a great analogy. And I think that's what makes this research so exciting. It has the potential to move GAN research from a sort of black art to a more rigorous and scientific discipline.
I agree. And that shift could have far-reaching implications.
Okay.
It could lead to more reliable GANs, GANs that are easier to train and less prone to those strange behaviors that have plagued the field for so long.
And that reliability could open up a whole new range of applications for GANs.
Right.
Applications where trust and predictability are essential.
Exactly. Imagine using GANs in areas like medical imaging or scientific simulations, where accuracy and consistency are paramount.
Right.
If we can develop GANs that are truly reliable, the possibilities are endless.
So to bring it all back to our listener, what's the one key takeaway you'd want them to remember from this deep dive into R3GAN?
I think the main takeaway is that GANs don't have to be these overly complex, unwieldy beasts.
Yeah.
By focusing on simplicity, theoretical grounding, and a well-designed loss function.
Right.
We can build GANs that are not only effective, but also elegant, reliable, and potentially transformative for a wide range of fields.
That's a great point to end on.
Thanks.
This paper is a reminder that sometimes the most elegant solutions are also the most powerful.
I agree.
And that's something worth thinking about.
It is.
No matter what field you're in.
Absolutely.
We hope you enjoyed this deep dive into the fascinating world of R3GAN.
It's been fun.
Until next time, keep exploring and keep asking questions.